And so for our first talk, I'd like to introduce Dr. George Halliwell. So George is from NOAA's Atlantic Oceanographic and Meteorological Laboratory, or AOML, and he's going to be presenting today on the Upper Ocean Forum representing using moving and stationary profilers. So George, are you on the line?
Yes, I am.
All right, let me pull up your presentation here and we'll get you started.
Thank you.
All right, welcome.
Welcome. Okay, thank you. Today I'm going to talk about upper ocean representation by the assimilation of ocean profilers, looking at the advantages gained by using gliders, moving gliders, versus assimilating profiles collected at fixed locations. First, I'd like to acknowledge my co-authors in this work. Next slide, please. This presentation is part of the AOML effort, and there are two other presentations from AOML researchers. Ricardo Dominguez will talk about the link between the upper ocean and 2017 Atlantic hurricanes. Matu Lehanaf will discuss the upper ocean conditions in the Gulf of Mexico during Hurricane Michael. Next slide. First, I want to point out that this work focuses on the open ocean, and in the open ocean, we need accurate representation of ocean mesoscale features if we're going to accurately predict SST cooling in coupled forecast models. And the correct representation of mesoscale features is important because these features are often associated with differences in upper ocean temperature and tropical cyclone heat potential. Plus, based on research by Nick Shea and Benjamin Jaimes, the dynamics of the eddy field affect the magnitude and pattern of SST cooling forced by hurricanes. And to look at these issues, first of all, the motivation, I consider two questions here up front. How effectively can the assimilation of ocean profiles by pilot underwater gliders represent mesoscale structure in ocean analyses? And second, does the motion of these piloted gliders provide significant additional error reduction in the representation of ocean mesoscale features? The spoiler alert is yes. And I'll be looking at observing system simulation experiments to address this issue. The high resolution representation of the truth provided by an OSSE system makes this possible. Next slide, please. Just briefly, OSSE system components. The nature run is used to represent the truth, and we used a high resolution run of the HICOM model to provide this nature run. The nowcast forecast system we use, the forecast model is also HICOM, but run with substantially different configuration from the nature run. We call this a fraternal twin OSSE system. We have our in-house data assimilation procedure, a statistical interpolation system that's designed specifically for HICOM Lagrangian vertical coordinates. And we have the synthetic observation simulation toolbox, which simulates the observations and adds realistic errors to them. Next slide. There are three main parts to this talk. First, I'll demonstrate the limitations of assimilating repeat ocean profiles collected at a single fixed location. And what I'll show in the OSSE results is that there's a very limited radius around any ocean profiler if it's sampling at a fixed location within which large error reduction can be achieved. I'll perform more rigorous statistical analyses in step 2, where I will deploy a large array of synthetic ocean profilers deployed at fixed location in the open Atlantic Ocean. And then to look at the impact of moving gliders, I'll also deploy a large array of gliders released at the same locations as the stationary profiles to demonstrate the positive impact of moving profilers or any moving platform to provide significant additional error reduction. As we're focusing on hurricanes, looking at two fields related to upper ocean temperature, TCHP, and then the average temperature between the surface and 100 meters. And also, because of the importance of resolving mesoscale features, I'm looking at the fields of dynamic height at the surface relative to 1,000 meters. Next slide. To understand what is happening, we run our DA system with a daily update cycle, and the analysis increment is calculated by the equation shown. The key point here is that the background error covariance matrix, which is tapered by a localization radius function, spreads the innovation through model space to determine the analysis increment for the correction of the model fields. And as a result, of course, you expect the greatest correction at the location of the profiler, but the error is increasing away from it. And the OSSE system will demonstrate how important that is. Next slide. Okay, first I'm looking at a case where I assimilate an ocean profiles of TNS at a fixed location twice during 2 analysis days. I begin with an unconstrained forecast model, and the location of the simulated profiler is shown. On the left, I show the nature run representing the truth minus the forecast model. And what that is the negative of the forecast model error. What that illustrates is the pattern of correction in tropical cyclone heat potential in this case that will be required to perfectly correct the forecast model. So with the OSSE system, you can visualize the errors very nicely. On the right, I show the combined analysis increment over the first 2 analysis days, and this shows the correction provided by the assimilation of the single profiler. And what you see, of course, is limited in radius from the profiler itself, but also, if you look to the south and southeast of the profiler, you see the correction actually has the wrong sign. So you expect errors in the correction to increase fairly rapidly away from the profiler. And next slide, please. But to look at this in more detail with more rigorous statistical analysis, I'm looking at a larger region in the ocean. This is within the western subtropical gyre, north of the islands and south of the Gulf Stream region, where we hope to see quasi-homogeneous statistics in the ocean structure and variability. And in this case, I'm assimilating daily ocean TS profiles at these locations shown, separated by 2 degrees. And I'm running the system from 1 May through 31 October 2014, assimilating synthetic ocean profiles generated from the nature run into the forecast model. And I'll be showing analyses that were performed over a 5-month interval, 1 June through 31 October. It's actually 5 months, not 6. Next slide. What we have over that 5-month interval, if you calculate the RMS error in 2 fields, this is dynamic height on the left and the average temperature in the upper ocean, 100 meters of the upper ocean, you see the RMS error pattern shows very clearly how the large corrections tend to be confined close to the locations of stationary profilers. You see a dotted pattern here very clearly in both fields. Next slide. So I run a similar set of experiments where at each of these release points, I release a moving glider that is shown on the right, executes a reverse figure 8 pattern at 0.25 meters per second, sampling TS profiles down to 1,000 meters. And I generate synthetic glider profiles from the nature run daily, again, and simulate daily over the several month period. And how does this affect the accuracy of the analysis? Next slide. The answer is very much. This shows the case for the dynamic height. The panel on the left shows the figure I showed before with the dotted pattern. But with the slowly moving gliders, and each glider probably takes about 45 days to execute that reverse figure 8 pattern once. So, but even with these relatively slow moving gliders, you can see that you're filling in the gaps in terms of reducing errors in regions intermediate between the locations of the gliders. The gliders are still separated by a nominal separation of 2 degrees, but the fact that they're moving and they're crossing gradients, each glider is tending to map out ocean structure in this vicinity. The cumulative effect is a much more uniform error reduction. Error variance for the stationary profiler is reduced by only 13%, but 54% by moving gliders. Next slide. Same figure for upper ocean temperature average. On the left, you can see the dotted pattern, but again, a much more uniform. Not quite as good as the for dynamic height, because advection is very strong in the temperature field, and it's harder to reduce errors in that field. But still, we see quite a much larger error variance reduction in the upper ocean temperature field, achieved by just assimilating profiles from platforms that move. So we see quite a bit of positive influence here. Next slide. Look at this quantitatively in wave number space. I calculated wave number spectra. The top right panel shows the zonal error squared coherence for 3 cases. The bottom panel shows the meridional error squared coherence. The black line, the black horizontal line near the bottom, which shows insignificant coherence, is the coherence between the unconstrained forecast model and the truth represented by the nature run. Of course, the eddy field representation is totally different and between the two in the forecast model. For simulating stationary flatworms, the red curve shows that you see, at least at longer wavelengths, you see significant error reduction and an increase in coherence. The vertical black line shows the Nyquist wave number, defined as roughly twice the nominal spacing between sensors, and you can see that significant error reductions is only achieved at wave numbers that exceed the Nyquist wave number, which is 450 kilometers in this case. But if you simulate moving gliders, not only is the error reduction or significance of error reduction increased substantially at all wave numbers, but you can see that the significant error reduction extends to smaller wave numbers than the Nyquist. The low mapping of ocean structure by the moving gliders is resolving smaller scales in the system and an overall more accurate representation of the mesoscale eddy field. Next slide. There's some interesting results in terms of how rapidly model fields adjust to the profiler simulation, whether they're stationary locations or moving. And the moving platforms do make a difference in how rapidly fields adjust. Next slide. Here we have a time series of RMS error beginning at 1 May, where the error is the same in all experiments as it is in the unconstrained model. And here you see the rate of error reduction as day by day we assimilate the observations. The red curves show the 2-degree separation case that I've been illustrating. And with glider assimilation, you can see at 2 degrees that there's a steady decrease in the RMS error that occurs over about a month. And whereas there's only very small or really not significant error decrease if you simulate stationary ocean profilers. The green curve shows another case I ran with 3.5 degree separation. And here with the simulating gliders, you do see a small but slow decrease in error that continues actually for about another month beyond what this figure shows. So you still see that it requires that medium to coarse resolution deployment of glider arrays. You still need time for the ocean to adjust to the pressure field. And this should point out, this is for the dynamic height field. If you deploy gliders at a very high resolution, and obviously economically unfeasible, you get a much better result, a very quick error reduction that's maintained, and even stationary profiler simulations. But at intermediate resolution, you see a distinct advantage from gliders that has needs time to accumulate. But there's a different reaction in the next slide, please. For the upper ocean temperature field, the response is quite different. No matter what resolution you deploy gliders or fixed profilers, you have a very rapid RMS error reduction over the first couple of days. And with gliders, the reduction that's achieved is maintained over time. But like stationary profiles, you see there's a couple of weeks of error growth that occurs that really negates much of the advantage you gained over the first 2 days. And this is a result that we found from our analysis of the rapid advection of temperature, nonlinear advection of temperature, which tends to increase errors gradually at locations between the locations of the fixed profilers. And this error increase is blocked by glider motion. So another advantage for gliders in resolving mesoscale structure of upper ocean temperature. Next slide. Okay, key findings. As I showed, gliders do give you a much better representation of mesoscale ocean features, both in the ocean pressure field represented by dynamic height and upper ocean temperature. And the moving platforms significantly increase the range of influence of simulated profiles to give you a much more even error reduction across any domain. Next slide. And again, with the time required, we see different behavior in the upper ocean pressure field and upper ocean temperature field, with gliders deployed at medium resolution, needing time to correct the errors in the ocean pressure field if they're deployed at medium resolution. Whereas correcting the upper ocean temperature can be achieved very quickly, but glider motion is required to prevent errors from growing over regions between the location of the simulated profiles. Next slide. Key future work. Our near-term planned future work is going to involve performing observing system experiments to evaluate the impact of real PHOG glider deployments that have been deployed. We've already run OSSEs for of the 2017 hurricanes throughout the Atlantic, and we've looked at OSSEs in the Gulf of Mexico for Hurricane Michael, as Matu will talk about later. But we are planning now to extend the OSSEs to the open Atlantic for the 2018 hurricane season, focusing on Hurricane Florence, and then the 2019 season focusing on Hurricane Dorian, looking at the impact of the gliders in comparison to assimilating other existing components of the ocean observing system. So I'll leave it at that. Thank you.
George, thank you. I think we have time for one question, and I think Dr. Stephen Howden asked, George, are the gliders assimilated along their track or treated as localized vertical profiles?
They are treated as localized vertical profiles because during the time the glider ascends or descends, it's over a horizontal range smaller than the model grid spacing. So you really gain nothing by following the track at all.
Great. Thank you very much, George.
Okay.
We appreciate it.
Thank you.